So, on the behalf of Chinta, I welcome you to this Cheng's the conference or the meeting session on the Cheng's conjecture. So, what to
Yeah,
you?
so today probably it will be the last session, and I am going to try to finish everything. So let's start. Mostly it will be by slides today, and if you have questions, just stop me, and I will be happy to answer. So okay, can you see the slides?
Yes,
Anyone?
it is visible.
Okay. Okay, great. So, am I audible clearly?
Yes, sir.
Okay. So, as a small recap, we talked about analytic functions on complex plane, and we said that there is this concept of biholomorphism that uh, basically is the complex analytic way of seeing whether two domains are really same for doing complex analysis or not. Now, we also had this Riemann mapping theorem, which says that what if you have a simply connected domain in the complex plane, which is not the whole complex plane, then it is biholomorphic to the unit disk, which basically means that there is only one possible such domain for doing complex analysis, which is the unit disk. This makes our life much simpler because then you only have to consider lesser number of geometric objects while you do analysis on it. So now we then introduced all these notions of several complex variables. We talked about the concept of holomorphic function, first d bar operator, and then the concept of holomorphic or analytic function in case of higher dimensions. And then uh, we actually gave examples where the Riemann mapping theorem fails in higher dimension. So we have the natural unit ball and the polydisk, which are the two obvious generalizations of the unit disk in higher dimensions, and both of them are simply connected. However, they are not biholomorphic to each other, which shows that the problem is much more rich and difficult in higher dimension. So for that, first we introduced the notion of pseudo-convex domains last time, that a domain is called pseudo-convex if these conditions are satisfied. Now you can think of being pseudo-convex as locally near a boundary point of the domain. So a domain has boundary. It's a compact domain. It's a bounded domain. So it's a bounded domain. It has a boundary, and in the boundary, around each boundary point, the domain kind of looks like a ball or a sphere, part of a sphere, and it's kind of convex. So, anyways, that is the definition of pseudo-convex. And then we had this theorem by Ban Wang that says that if G is biholomorphic to the unit ball if being equivalent to any of these conditions below, which means if any of these conditions hold, then G becomes biholomorphic to the unit ball, which is really something that is like Riemann mapping theorem in higher dimensions. And in that case, this is one of the theorems that we have in multivariable complex analysis, which is like Riemann mapping theorem. So now the question is, do we have more such theorems? Do we have more such theorems basically, which actually will tell you complex domains being biholomorphic to the unit ball? The answer is, in short, yes. This is not the only theorem, unlike one dimension, where we have the Riemann mapping theorem. In higher dimension, we have many such theorems which will tell you that something is biholomorphic to unit ball. So for that, let us go towards that. First, you have to define, there are many ways to do it. You don't necessarily have to define this. But one way of attacking this problem is defining these quantities that we are going to talk about now. First of all, suppose we have a bounded domain in Cn, then we can define a Bergman space of functions. How do you define that? F is, but the Bergman space is denoted by A2 of omega, if omega is our domain. It is a space of functions f which are holomorphic, which are complex analytic in the domain, and whose mod squares integral is finite, or the L2 norm is finite. Here the dV is basically the volume measure, or you can think of some sort of volume form. So we have talked about integrals of forms, so you probably know what it is. So basically, it's all the holomorphic functions whose mod square integral is finite. Then, and then the thing is, because it is a subspace of the L2 space, L2 space basically means the functions where this integral is finite. There we don't have the condition that f has to be holomorphic. However, this space A2 omega is actually a closed subspace of the L2 space, and L2 has this inner product structure. So A2 omega also has an inner product structure, which is like this, which is just inherited from the L2 space because it's a subspace. Then, once you have this inner product structure, first of all, you have A2 omega as a Hilbert space, which is basically inner product space. Separable is a condition that you don't have to know right now. It's a vector space, so it has a basis. If it has a basis called phi j, now this basis can be infinite in number because it can be infinite dimensional. But if you have a basis called phi j, then you can look at this sum. Actually, there would be a conjugate on the second sum end here. And if you can look at this sum, and on compact subsets, this sum of functions will actually converge to a function. You can prove it. And once it does, then that function that it is convergent to is called the Bergman kernel. Now, if you know a little bit of now if you know a little bit of Hilbert space theory, then look at the evaluation functional for any function in this Bergman space, and there is a correspond by Rie's representation theorem. There is a kernel that represents, because we have an inner product structure on the space, there is a kernel that produces this functional. So that's why that kernel is also called the Bergman kernel, and in fact, this sum actually converges to that kernel only. You can prove that. Now, you might think that it is a very difficult definition. I mean, it's not very difficult, but it's definitely something new in case you haven't seen something like this. However, what makes this thing very interesting is if we have a biholomorphism between two domains, then the Bergman kernel of one domain changes in this way with respect to the Bergman kernel of another domain. And then however, once you have this property star, there are implications of this property. You might in the first look, this property might seem like you might not understand why am I stating this property, but let's go to the next slide to understand that. So once you have the Bergman kernel of omega like this, you can put z equal to zeta in the Bergman kernel. Basically, you are taking zeta, z and zeta are both ranging in the domain. If you put them to be the same variable z, then you get a function, you take the log of the function, and then you take PD bar of that, or which means this partial derivative, second order derivative. There you see that there is a metric. This Gij that comes by the dd bar of log k omega is basically a metric on the domain. We talked about metrics before when we talked about differential geometry, and this is a very similar metric. It's a Hermitian metric which tells you what did metrics do before? Metrics tell you the length of vectors, like the inner product between vectors. So this will do the exactly same thing. It will tell you the inner product between two complex vectors on the domain, tangent vectors. But this metric has another very interesting property. The property is, if this property star here comes from the property star of Bergman kernel that says if we have two domains which are biholomorphic by a map F, then the Bergman metrics are they're isometric. Which means what? It means that the length, basically it means that if you look at the distance between 2 points on the domain omega 1, like call the points P and Q, and then look at the images of those 2 points, FP and FQ in omega 2, then the distance between those 2 points P and Q in the domain omega 1 will be same as the distance between the 2 points FP and FQ in the domain omega 2, provided the metric used there for both the domains are the Bergman metrics. So Bergman metric does not see changes under biholomorphism. Now this is something very important because I have emphasized this again and again, that in complex analysis, you really deal with things, you want to deal with things that are biholomorphic to each other. Because two domains are biholomorphic means they are complex analytically exactly the same things. So Bergman metric actually tells you that yes, Bergman metric also does not see any difference of two domains which are biholomorphic to each other. So it actually serves the purpose of complex analysis. So basically, but because of this reason, in complex analysis, Bergman metric is an old and a very powerful tool to analyze the geometric properties. It's a metric, so it is definitely like related to Riemannian geometry, as we have talked about before. And at the same time, it carries the essence of complex analysis that if two domains are biholomorphic, this metric will not see any difference. There are other metrics, by the way. Just
excuse me for the interruption. So something like one of our students in between raised a hand. Probably he got a doubt. Gurnur, can you please carry on?
Yeah.
Sir, I just wanted you to go back to the last slide from home.
Yeah. Yeah.
Gurnur? Hello?
Hello?
Yes, sir.
Yeah. Is this the slide you are talking about?
Yes, sir. Like, I just wanted to have a screenshot of it. Thank you.
You don't have to take a screenshot. If you want, I can give you the slides later. Okay. Anyways.
Thank you, sir. Yeah.
The thing is, just tell Ashonida and I will give it to Ashonida. Okay. So, anyways, so this is the idea of Bergman metric. Now, similarly, just like we have it for complex domains, you don't have to like go into too many details here, but we have a Bergman space on complex manifolds also. We introduced the notion of complex manifolds already. So on complex manifolds also, we have a Bergman space, which is exactly the same thing, but instead of functions, now you have N0 forms, holomorphic N forms, such that their inner product with themselves is less than infinity. That is the definition of L2, like being L2. exactly like before, we have a inner product on the Bergman space. Again, this is an inner product with forms, so that's why wedge product and these kind of things are coming into picture. Don't worry about them. Just think that they are very similar to the one that we have in domains. So exactly in the case of, as in the case of domain, you can think of the Bergman space on a manifold, and there you take the basis of the Bergman space, take the wedge of the basis with itself. I mean, of course, in one case you do conjugate, in another case you don't do conjugate. And on compact subsets, this sum actually converges to a NN form, which is called the Bergman kernel form. The only difference between the previous Bergman kernel and this one is, this is an NN form and the previous one was a function. But you know that locally, in local charts, since a manifold looks like Cn, a form also looks like a function. And that is really the Bergman kernel function. So it's a form which locally looks like a Bergman kernel function that we saw before. Now, this is exactly the same thing. If we have a local coordinate, in the local coordinate, the Bergman kernel form will look like a Bergman kernel function times some volume form. This is a volume form. Now, once you have this Bergman kernel form function, you can take dd bar of that, just like we did for the case of domains. You can take dd bar of that and you get a metric. This metric is called the Bergman metric of manifolds. And this metric is actually independent of local coordinates. Why am I saying that? Because this k star is obtained in a local coordinate. So you might think that if I take dd bar of that, I will get something that depends on the local coordinate z here, but it actually does not. And there are several important properties of Bergman metrics on manifolds. One important property is that if you have more than one co-dimensional submanifold, then Bergman matrix does not see that. Which basically means that if you have a manifold, and if you have a submanifold which has more than one dimension lesser than the dimension of the manifold, then the Bergman, let's call this submanifold as n, and let's call the bigger manifold as m, then the Bergman kernel on m minus n is basically the same as the Bergman kernel on m. And since the Bergman kernels are the same, the Bergman matrix are also the same. So if you take out submanifolds with one or more codimension, you actually don't see a difference in the Bergman metric. Why is this important? It will all come later. Now, this is a section that I'm going to skip right now because we might run short on time. So let's skip this section. Now we come to the crux of the hour, that is the main topic. This is my research topic. So now we will introduce several notions in complex geometry, and we will see this notion of Bergman kernel with it, or Bergman metric with it. And at the same time, we will also try to see theorems that are very similar to Riemann mapping theorems. So let's go one by one. On a complex manifold, a Kähler form is a differential form that looks like dd bar of rho. If you take dd bar of rho, it's a 1-1 form, and rho is a real smooth function. So any form that looks like locally dd bar of some real function is a Kähler form. And if you have a Kähler form on a manifold, it is called a Kähler manifold. Now, from any different 1-1 form, you actually can get a metric. Now, this is something that there is a formal way of doing it, but let me just try to indicate this in easier terms. So just see, let me see. So suppose Yeah. Can you see my one, like a blank screen?
Yes.
So suppose you have a 1 form, which is dd bar of a real valued function rho. The corresponding metric would be, so this is local. The corresponding metric would be locally del square del zi del zj bar of this function rho. This is a matrix because this is gij. So this is a matrix, depends on I and j. Ij vary between 1 to n. So it's a matrix, and you are calling it a metric because it's positive definite. You can check it, and also it can measure the length of vectors. If you multiply wi, gij, wj, where w is a vector, and do ij like this, you actually write it like this, the j bar, because of the bar here. If you write it like this, then this will be telling you the length of the vector square. So you actually can measure length of vectors with this kind of an object. That's why it's a metric. I mean, it also has other properties, but this is the main property. So then let's go back to the slides now. Once you have a Kähler form, you can get a Kähler metric from it. So basically, now, so basically, what is a Kähler metric? Kähler metric is something that locally looks like dd bar of a, or del square del zi del zz bar of a real smooth function. Now, what is the definition of Bergman metric? If you remember, for a domain or a manifold, Bergman metric is obtained by dd bar of log of this k omega of zz, where k omega is the Bergman kernel. So log of k omega zz is like our function rho that you need for the Kähler metric. So you see, by definition, Bergman metric is scalar. In fact, Bergman metric is the first known Kähler metric. So Bergman metric is the Kähler metric, and it is by definition Kähler. Now let's come to Einstein's equation. This is something that you deal in general relativity. This is the most general form of Einstein's equation, and this is exactly the reason for which I had to introduce the notion of Ricci curvature, scalar curvature, and so on. This is Einstein's equation, where it says the left-hand side, the R mu nu is the Ricci curvature, R is scalar, G mu nu is metric tensor, lambda is a constant, K is a constant. So the left-hand side basically tells you the curvature of space-time. This is a curvature. And the right-hand side is T mu nu. What is T? T is stress energy tensor. It basically tells you how much matter and energy is present at a point of space-time. So basically, I think many of you have seen popular science videos where you have seen that in general relativity, presence of matter curves space-time. For example, if you have a black hole, in that case, it is so dense and so massive that the space-time is curved and even light cannot come out of it. So that is exactly manifested in this equation, because the right-hand side is a quantifier of how much matter and energy is present, and the left-hand side tells you how much curvature is present. So curvature depends on the the amount of matter and energy present. Now, we have, this is the Einstein's equation in full generality. In vacuum, however, when you have vacuum, what does vacuum mean? Vacuum means that there is no matter or energy present. So in that case, the right-hand side becomes 0. Once you have the right-hand side become 0, you can take this equation with the right-hand side being 0 and convert it to an equation of this form. How? You take the equation, take the right hand side to be 0, and take trace of everything. Now, I have introduced the notion of trace before. So you take trace of everything. The trace of the Ricci curvature is a scalar curvature, and the trace of the metric tensor is the dimension of the space, which is D. So if you take the trace of this equation with 0 on the right hand side, you get this equation. And then solve for R becomes this, and then put R back in this equation here with the right hand side being 0. Once you put R back, you basically get this equation, which is called the trace reverse form of Einstein's equation in vacuum. We are going to tell it the TREF. Now, on a complex manifold, a Kähler-Einstein metric is a metric that is scalar, which we already know what it is, and which also obeys the TREF. It's a very special metric. This metric enjoys a lot of properties. That's why it is studied in complex analysis, in complex geometry, and even in algebraic geometry, like complex algebraic geometry. And now, there is this famous theorem by Cheng and Yao, and also Mock and Yao, where they say for a bounded pseudo-convex domain with reasonably smooth boundary, there is a natural. Natural means it comes somewhat naturally by solving a set of PDEs. A complete, we know what a complete metric is. A complete Kähler-Einstein metric, which means whenever you have a bounded pseudo-convex domain, you can just give it a metric, which will be natural. I mean, kind of coming intrinsically. It will be complete. It will also be Kähler-Einstein. So many properties in one metric. We call this metric as the Cheng-Yao metric. The Cheng-Yao metric for a domain is unique up to scaling. For the unit ball, for example, the Cheng-Yao metric is precisely its Bergman metric. Now, the next question is that where else? So for unit ball, they are the same. Bergman metric and Cheng-Yao metric are the same. So for which other domains are they same? So there is a famous conjecture by Yao, which says the Cheng-Yao metric of a bounded pseudo-convex domain is precisely its Bergman metric if and only if the domain is a bounded homogeneous domain. Homogeneous means automorphism group acts transitively. Don't worry about the definition. We talked about the definition before, but don't worry about it now. Then, previously, if you remember, we talked about this theorem called Ban-Wong's theorem, which was a theorem that shows you biholomorphism to unit ball. Now, using this theorem and Yao's conjecture that we just saw right now, one can make a special case of this Yao's conjecture, that what happens if we have strictly pseudo-convex other than pseudo-convex. Then, if you assume strictly pseudo-convex, then you get a conjecture called Cheng's conjecture, which says Bergman metric of a bounded strongly pseudo-convex domain with smooth boundary is Kähler-Einstein, which basically means that it is the Cheng-Yao metric, if and only if the domain is biholomorphic to the unit ball. So see, it is such a strong theorem or a conjecture. In fact, it also shows you biholomorphism to unit ball, which is something that we wanted to attack. So this was solved completely by Fu, Yang, Nemirovsky and Shafikov, and Huang and Zhao. Xiao is my co-advisor. So they solved this conjecture completely in all dimensions for domains. In fact, it follows from another famous conjecture called Ramadanov conjecture, which we are not going to cover today, most likely. Now, this is the Cheng's conjecture for domains in CN that has been completely solved. But the question is, can you generalize Cheng's conjecture to manifolds? Because we know that this Cheng's conjecture is about Bergman metric, and you can define Bergman metric on a manifold also. So there, you can define Cheng's conjecture for Stein manifolds Stein manifolds are basic. This is the definition of Stein manifolds. It looks like a mouthful, but the definition really means that it has, first of all, it's a generalization of pseudo-convex domains. It is something, it's a manifold, but it acts like a pseudo-convex domain because of the first condition. And the second condition tells you that there are many, many holomorphic functions on a Stein manifold. So so the question is whether the previous conjecture can be generalized. The previous conjecture was about pseudo-convex domains. So you need to have something which is like pseudo-convex domains. Stein manifolds are like that. So you try to generalize, obviously, this conjecture to Stein manifolds. And there, Huang and Lee solved this conjecture for Stein manifolds that says the only Stein manifold with smooth and compact, strongly pseudo-convex boundary where the Bergman metric is Kähler-Einstein is the unit Borg up to biholomorphism. So basically for Stein manifolds also, you see that Cheng's conjecture holds. Now, that there is a next set of generalization. So you see that previously Cheng's conjecture was about domains in Cn. Then it became about Stein manifolds. Now we can generalize this even further. So now the question is, can something be said when we have singularities in the Stein manifold? You can just think of a singularity where
Sir, you are not audible.
yeah, sorry. So the thing is, when we have singularities, what do you mean by singularities? Now it's hard to understand what do you mean by singularities. Okay, let's try to give an example by drawing some pictures. I think it's best to draw pictures here. Look at this curve. This curve is smooth everywhere, right? But look at this point here. Let's call this point the origin. You can make this curve pass to the origin. This curve here has a problem. It intersects itself. So that's why when you try to define tangent vectors, you can draw this kind of a tangent or this kind of a tangent. The tangent vector at this point O is not very well defined. Then we have something, we have something like this. Suppose let's draw something like this. Here also you see, you can draw tangent vector like this. You can draw tangent vector like this in some sense. I mean, they will be similar, but try to, I mean, if you come from this side, you have a tangent vector. If you come from this side, you have a tangent vector. So then at this point of this, at this pointy region here, this curve is called, that it is said that this curve has a singularity. So once you allow singularities in the Stein manifold, it becomes something called a Stein space. I mean, if you know algebraic geometry, it is like a variety. This is also a variety, by the way. This is also a variety. A variety is basically a zero set of a polynomial. You can write a polynomial equation that defines this variety actually. I think in JE also it is sometimes taught. So Then the thing is, that once we have a variety, there can be this kind of singular points in a variety. A variety may not be always smooth. So just like that, let's now go back to the slides. I'm sorry, I am like shuffling between the slides and the OneNote because you cannot write on the slides in Google Meet. So the thing is, now basically when you allow singularities like the previous thing that we showed, if you allow singularity in the Stein manifold, you have a Cheng's conjecture for Stein spaces where singularities can happen. Second, now, if we have a Stein space with isolated normal singularities and compact smooth boundary, then Huang and Lee proved, don't bother about this condition, CR equivalent to algebraic CR manifold, don't worry about it, right? If we have a Stein space with isolated normal singularities, with normal singularities, there are meanings of these kind of things. Isolated means that these singularities do not reach the boundary of this Stein manifold. And normal singularities means basically the singularities have lesser dimension than the dimension of the manifold. Like when we drew that infinity symbol, the singularity was at a point which is 0 dimensional, but the curve is 1 dimensional. So the singularity has lesser dimension. So normal singularities basically mean something like that. So when you have these kind of singularities in a Stein space and the boundary is smooth, then Bergman metric on the regular part, which regular part means the part without the singularity, if Kähler-Einstein means omega is actually biholomorphic to a ball quotient. See, this is something interesting. Previously, Cheng's conjectures were about balls. However, now since we can have singularities, you can have quotient of the ball by some group. When you quotient a space, you normally can expect singularities in that space. And gamma here needs to have these certain conditions, finite, fixed point free. Fixed point free simply means that you can think of this group gamma as embedded in the unitary group, and in unitary they are matrix groups, right? So they have eigenvalues. Unitary simply means that in the matrix group, for any non-identity matrix, all the eigenvalues would be not equal to 1. So basically, now ball quotients can come into the picture, which makes this problem different from previous, because previously it was only about ball. However, now one may ask, are all ball quotients necessary? Or is it still true that for Stein spaces, we actually get biholomorphism to unit ball? See, this theorem here says that it has to be a ball quotient, but this theorem can be refined probably. That is the Cheng's conjecture, that you don't need all ball quotients. It actually is biholomorphic to unit ball only. So there, Ebenfelt and Xiao are my advisors. They proved that when we have gamma to be an abelian group, then the ball quotient doesn't have Kähler-Einstein Bergman metric unless gamma is a trivial group, which means when gamma is abelian, this ball quotient has to be the ball for it to have Kähler-Einstein Bergman metric. Now the question is, what happens when gamma is non-abelian? So when gamma is non-abelian in 2 dimension, the list of all groups that can act on the ball without fixed points, the all finite groups, is this. So this list was given by Milnor, who is a great mathematician. And This list is quite old actually. So this is the list of abstract groups in terms of their generators and relations that will act on the unit ball without fixed points. Now, for the abelian case, the abelian case is also there actually in this case. See, look at point number 1, group 1, and look at point number 7, direct product of any of these group with the cyclic group of relatively prime order. Basically, it says that all the Z mod P's are kind of okay here. And second, and so you see that then you see that this is the list only in 2 dimension because it acts on S3. So in S3 is the boundary of the unit ball in complex 2 dimension, because complex 2 dimension means real 4 dimension, and S3 is the boundary of the real 4 dimensional ball, right? So these are the groups. Now the question is whether we can show that other than the point 1 here, which is the group, the trivial group, if you quotient the ball with any of these groups, the Bergman metric on the quotient will not be Kähler-Einstein. Can you show that? And the answer is yes. That is what we showed. And that is by which Cheng's conjecture in 2 dimension for Stein spaces has been solved. So these are the theorems that we proved, that if you have a 2-dimensional Stein space and the CR equivalent condition, don't worry about it. If the Bergman metric on the regular part of the Stein space is Kähler-Einstein, if and only if omega is biholomorphic to B2. However, so what was the catch? Previously by Huang Li's theorem, it can be a ball quotient. And now we said, no, it cannot be the every ball quotient. It can be only the unit ball in 2 dimension. And then don't worry about the theorem 2 here. It's a bit too technical. Forget about it. So basically proving theorem 1 is same as proving theorem 3, where theorem 3 says that for any fixed point free finite subgroup, the regular part of the ball quotient has a Bergman metric if and only if gamma is identity. See, one direction is clear. If gamma is identity, the ball quotient by identity is basically the ball itself. And there we know that Bergman metric is Kähler-Einstein. Now, the other direction is something that you have to prove. What are the gamma that are possible? The gamma possibles are from this list. So you basically, what do? You take all these groups, look at the ball quotient by these groups. For each of these groups, you show that the Bergman metric of the ball quotient cannot be Kähler-Einstein. See, Bergman metric by definition is scalar. So what do you mean by not being Kähler-Einstein? It basically means it doesn't obey the Einstein's equation, or the equation that we called as TREF. So one can, first of all, let's look. So this is the Kähler-Einstein equation. This is the Ricci curvature. C is a constant, and this right-hand side is the metric tensor. That was the TREF. I am just writing it in a different way, but they are exactly the same thing. Now, one can express the Kähler-Einstein equation on the ball quotient in such a jumbled format, and don't worry about the format. It will be simplified soon. So if it is Kähler-Einstein, then this equation has to satisfy. This is the Kähler-Einstein equation for ball quotients, where these gammas are basically like the gammas are actually varying in the group, capital gamma. The small gammas are varying in capital gamma, the group. So now the Kähler-Einstein equation is actually like this. This is the simplified version. Right hand side is phi x to the power 4, where x is between 0 and 1, and phi x looks like this. although it has complex matrices in the expansion, it will be a real analytic function. You can prove it. And the left-hand side of the equation would be fx to fx, where f is this. And the matrix determinant of the matrix A is this. Okay? Next. So basically, what do we have to prove? That for any of the ball quotients other than the trivial group, this equation fx equal to phi x to the power 4 does not hold. If we can prove, then we have solved the Cheng's conjecture. So how do you do that? Well, first of all, you see that Milnor's list is enough to consider because he has given all the fixed point free subgroups. He talks about orthogonal action. We are interested in unitary action. The group has to be unitary, but don't worry about that because unitary group is embeddable in orthogonal groups. So you can find unitary representation or try to find unitary representation of these groups. In fact, all of these groups have unitary representation. So now, so basically what is the recipe of solving this problem? You have this group. You try to find what would be x and y in terms of these generators and relations if they satisfy these relations and they are unitary matrices. Try to find those matrices x and y. Once you know, then you can generate the group in terms of x and y. Once you can generate the group, you can look at this Kähler-Einstein equation in terms of the group elements and show that the equation doesn't hold. So this is the formula. Now there is a small catch here. If by any means this gamma can be embedded in SU2, simple unitary groups instead of unitary group, you can directly say that it will not be Kähler-Einstein unless gamma is the trivial group. There is a reason behind that. Let's not talk about it right now. We are running short on time. However, if gamma is not embeddable in SU2, then you have to do some painful calculation. And what is that? So basically, you have the equation Kähler-Einstein to be fx equal to phi x to the power 4. And you can check because identity matrix is present. If you take x tending to 1, both sides will blow up. Okay? So both sides will blow up. And then what you can do, so why are both sides blowing up? Because both sides have term which is of the power of 1 by 1 minus x. Just put gamma to be identity matrix and you will get that. So you see, because of 1 by 1 minus x on both sides are blowing up. But if the equation doesn't hold, then if you take a Laurent expansion of both sides with respect to 1 by 1 minus x, if the equation doesn't hold, then there should be some power of 1 by 1 minus x whose coefficient would be different on both sides because they are not, both sides are not same. So basically, in case you don't know what a Laurent expansion is, think of two functions and think of the Taylor series of both the functions. If the two functions are not same, then their Taylor series cannot be same. So there should be some Taylor coefficient which should be different on both sides. So in this case, we find that coefficient. This is the coefficient of 1 by 1 minus x to the power 8. And we say that for any of the groups that we have in Milnor's list, this coefficient, other than the trivial group, this coefficient is not 0. But this coefficient, it is 0 means that you take one side of the equation to another side and make a coefficient out of it. It should be 0 if the equation is satisfied, but we prove it is not 0. And to prove it is not 0, you actually have to prove this lemma. By this lemma, which is basically summing over roots of unity, which is something that you all are familiar with, you have to prove this lemma Once you can prove this lemma, you actually can prove that this C gamma will be non-zero for any of Milnor's list if you put the groups other than the trivial group. If the coefficient is non-zero, then obviously the equation does not hold, and hence you have the Kähler-Einstein equation holding not holding in case of all the non-trivial groups. That is exactly what we wanted to prove in Cheng's conjecture for Stein spaces in dimension 2. And you can ask, what are the future directions? You only prove Cheng's conjecture in 2 dimensions. What about the higher dimensions? The question is, the main observation is that this 2 dimension was possible because of this Milnor's theorem, which gives us an explicit list of all the groups that can act on the unit ball in 2 dimension without fixed points. Do we even have such a list in higher dimensions? The short answer is yes, we have. However, the long answer is no, because the list there is not at all explicit. We have lists, but the lists are not very easy to work with. This list is very convenient. You can directly assume x and y are unitary matrices, and from these relations you will get expressions of x and y. But for the higher dimensional analogs, first of all, there is finding a general format of unitary matrices is hard. And even if you have that, the groups do not look very well. So there, proving this theorem, Cheng's conjecture for higher dimensions for Stein spaces becomes a challenge. But I hope somebody can take up this challenge soon and can solve this. Anyways, this was my talk. Thank you for having me for this mini lecture series. And in case you have some questions, please feel free to ask.
Sir, could you please again show the slide of the references?
I can give you the slides, but okay.
No, sir, just I will take it like a screenshot is very quick. That's why.
Sure. I like the enthusiasm that Gunnar has, and I hope he pursues a career in mathematics. These are the references. This is the slide number 1. This is the slide number 2. And this is the slide number 3.
Thank you, sir.
Any question? From anywhere?
I have
Yeah, sure.
several. So that theorem was for all dimension, that the Stein space which have the only Kähler-Einstein metric is the Bergman metric, has to be of the form b to the n quotiented by
Yes, that's true for all dimensions.
That is true for all dimension.
Yeah, so I think you are talking about this theorem by Huang
Yeah.
Li.
Yeah, right.
This is true for all dimensions. The question is whether you can refine this theorem. This says that
Right.
if it has Kähler-Einstein, then it has to be a ball quotient. But does it have to be all the ball quotients? In 2 dimension, the answer is no. It has to be only the trivial ball quotient. All the other ball quotients are not Kähler-Einstein. They do not have Kähler-Einstein Bergman metric. So the question is
Right.
whether you can generalize this in higher dimensions or not.
But the conjecture is it has to be, again, gamma has to be trivial in
Yeah.
higher dimension as well.
Yeah. And already, by the way, I think I also mentioned that Ebenfelt Zhao proved this already for gamma being abelian. If gamma is abelian, then none of the ball quotients can have Kähler-Einstein metric for all dimensions,
I
provided gamma is fixed point free finite abelian. It cannot have Kähler-Einstein other than gamma being trivial. So for abelian case, yes, that is already proven. But the question is, if you have, I mean, we obviously in Milnor's list only we saw so many of them are non-abelian. So the question is, what happens? What are the groups that are, first of all, can act explicitly? And even if you have them, how do you prove for the non-abelian case for a higher dimension? It's still open. We are working on it, but I mean, I don't think we are in a position to claim any result right now.
So the Bergman, okay, because this is new, just some basic questions. So the Bergman metric was something which is preserved by biholomorphic map. That is the importance of the Bergman metric.
Yeah.
And
I mean,
okay.
Bergman metric is, it's not preserved. It becomes an the Bergman matrix becomes an isometry. I mean,
Okay.
at biholomorphism,
Yeah.
it is an isometry of Bergman matrix.
Right.
Yeah.
So is there examples where they are not same, like Bergman metric and so Bergman metric is always scalar, you said, and then so are there examples where it's not like Einstein metric?
Yeah. Many.
Okay.
There are examples. I think worm domain doesn't have Kähler-Einstein Bergman metric. There are, I'm sure there are. I mean, I am 100% sure. I mean, in fact, if you take a general pseudo-convex domain, not strictly pseudo-convex, there only you can find Bergman matrix, I'm pretty sure, which is not Kähler-Einstein. Like, for example, if you, in few lectures back, when I talked about pseudo-convex domains, there this kind of a domain came. Let me show you this one, omega, here in the slide. This omega here is a pseudo-convex domain, which is not strictly pseudo-convex. It has a Bergman kernel. You can define Bergman metric, but I'm pretty sure, and I have a hint it's not Kähler-Einstein. In fact, like, I mean, Yau's conjecture, I mean, Cheng's conjecture doesn't even deal with this kind of domains because this is not strictly pseudo-convex. Cheng's conjecture is about strictly pseudo-convex. However, well, actually, you know what? In this case, Bergman metric probably will be Kähler-Einstein because of Yau's conjecture.
Yeah, what was the Yau's conjecture again? You mentioned
Yau's
something.
conjecture says that for bounded pseudo-convex domains with smooth boundary, Bergman metric is Kähler-Einstein if and only if the domain is a homogeneous domain, which means the automorphism group acts transitively on it. Now, I think for these kind of domains, the automorphism group does act transitively. So in that case, probably the Bergman metric is Kähler-Einstein, but I'm sure there are domains where the Bergman metric is not Kähler-Einstein. I mean, there can be very bad-looking pseudo-convex domains which are not strictly pseudo-convex. So there, you will have non-Kähler-Einstein Bergman metric. Yeah. In fact, yeah.
I see.
In fact, I'm wondering, you can define Bergman metric on polydisk, and probably it's I'm not sure. Probably it's not Kähler-Einstein. Yeah, probably it's not Kähler-Einstein.
So the Einstein that equation that was defined only in the context of complex manifolds. What were the spaces on which
You can define it for manifold.
or just manifold? Okay.
Because it's a manifold defined on a Ricci curvature of a manifold, right? So
Right. Okay.
it is defined in terms of a manifold, but for Stein spaces, when you have singularities, you just define it outside the singularity. Outside the singularity, Stein space is a Stein manifold. So you can define just on the regular part of the Stein space, which is a Stein manifold. And there you can define the equation just like before. So yeah, Einstein's equation still makes sense. Because if you remember, I said one thing, that when we have this kind of a theorem, that when we have a Bergman metric or Bergman kernel does not see smaller dimensional submanifolds. If we have a smaller dimensional submanifold, you can take it out of the manifold, then also the Bergman kernel will be the same. Now, for Stein spaces with isolated normal singularities, as I said, normal singularities mean the singularities have lesser codimension, higher codimension, less dimension. So you can
Right.
take out those singularities and the Bergman kernel will be the same because of this
Yeah.
theorem. So that is why, that is the motivation for defining the Bergman kernel for a Stein space only on the regular part. Because you can think of the irregular or the singular part as a smaller dimensional submanifold, and Bergman kernel doesn't see a difference in that. I mean, the implications, the reason for which this is true is because of there are theorems like Riemann extension theorem, Hartogs theorem. Because of those theorems, it actually is true. You can extend past such singularities. Even if you have a function defined around that singularity, you can extend past the singularity holomorphically because it is so less dimension.
Okay. And did you say what a state manifold is? Right? Is
Yes,
it
Stein manifold, the definition was written, but it's a bit convoluted.
okay?
Stein manifold.
Then maybe I don't want to know.
That's fine. Stein manifold, this is the definition. The first definition is basically definition of a pseudo-convex domain. Pseudo-convex domain can also be defined in terms of this property. In terms of holomorphic convex hulls. This is an alternate way of defining a pseudo-convex domain. So the first property tells you that Stein manifold is just like a pseudo-convex domain. The second property tells you, because of the Liouville's theorem, if you have a compact manifold, compact complex manifold, then you do not have non-trivial holomorphic functions on it, right? The holomorphic functions become constant. But the second assumption here tells you it has a lot of holomorphic functions.
I see.
So this is not a compact manifold, as you see.
Right. So it has to be open, like it cannot be quantum.
In fact, you can think of Stein manifold. Stein manifolds are already embeddable in Cn for some n. So you can think of them as a open submanifold of Cn.
I see.
It's a theorem that says every Stein manifold is. In fact, if you look at one-dimensional manifold, then there is a theorem, I think, in some algebraic geometry book, that every non-compact Riemann surface is a Stein manifold. So you see that it has to be Stein manifold kind of assumes it's non-compact. Otherwise, you cannot have the second condition.
Right.
Yeah.
Okay. Well, great. Thank you so much.
Absolutely.
Yeah, thank you, Soumya, for this wonderful talk.
Yeah. Okay. I hope it was helpful. And in case anybody needs the slide, just let Ashwanita know, and I can give it to Ashwanita. By the way, Raman, your name is actually Ramanujan.
No. My name is Shubhadeep.
Shubhadeep. Achha. So the thing is, there are mathematicians whose name is Ramanujan even now. In UCSD only there is one student whose name is Ramanujan. He's a number theorist.
Yeah.
So,
oh wow.
I know, too much expectation to live
Yeah.
to live with. So the thing is, Shubhadeep, are you in Kolkata right now?
Yes, I am in Kolkata right now.
Okay, I was planning to visit Chinta actually.
Yeah, sure. So when are you coming?
I'm coming on. Let's stop the recording and talk about it.
Yeah, sure.